Okay, so let's talk about how, for example, a keyboard process, the interactions between the hardware keyboard and a user mode wanting a key from the user might interact. So at the top, we have a user program that has a read key instruction in it. So that's just another level of macro that corresponds to SVC 3 or something. I don't know the exact number, but it's one of the supervisor calls that we can make. And it expects the next key from the user to be returned in register 0. So the code immediately following read key would assume that after the read key, which is an illegal operation, so that traps to the kernel, and after we resume execution, it expects to find the ASCII character from the keyboard in R0. Down here we have the actual hardware keyboard, which when you type a new key will interrupt the operating system, and the interrupt handler will basically read that character from the keyboard. Actually, typically what you read from the keyboards is a key number, and whether it's an upstroke or a downstroke on the key. And then the kernel runs a little bit of code to turn that appropriately into the appropriate ASCII character, depending on what, using the US keyboard or the Dvorak keyboard or the Egyptian keyboard or the Chinese keyboard. How to translate keystrokes into characters is under the control of the operating system. And then finally that information is stuck in a little circular buffer in the kernel. So as you type keys at the interrupt level, the kernel is typing them in. Anybody know what happens if you type too many keys and no one's reading them? What happens on your machine? Type, 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 type. It goes beep. So that's basically the kernel sort of telling you, look, I've filled up my little circular buffer. I can only hold so many characters. And if no one's reading them, I'm not going to listen to the keyboard anymore until one of the programs starts reading them. Okay, but meanwhile, until you hear the beep, you can assume that the kernel is saving away each character you typed in anticipation that some user program now will access the keyboard. So now we finally start running the program, and we execute the read key supervisor call, which is, as I say, an illegal operation. So that traps to the operating system, which determines that, in fact, it has that magic 1 opcode. It looks in the bottom bits to determine exactly which handler should deal with it. So it will go to the read key handler. And the read key handler's job is to basically remove the character from the buffer and return the character in R0. So it will go ahead and stick the character into R0, and then it resumes execution of the program, in a sense, having done the illegal operation. The goal of the illegal operation was to put the next keyboard character into R0. That happened. And so now we just resume execution at the PC +4 that was saved away, which is the instruction following the read key. Right, so we have these sort of cooperating things happening. We have the kernel dealing with the hardware interrupts from the keyboard, filling up a kernel buffer, and then we have a way in which user programs through supervisor calls can get information from the kernel buffer. So the kernel is sort of the intermediary here in the transaction between the keyboard and the user programs. Okay, so keep in mind that the program itself is paying no attention to the hardware. It's just assuming that it can go off and read a key from the keyboard anytime. What should happen, by the way, in the user program that did a read key if there's no character available? What would you do if you were the operating system designer? There's no character to return. So you should maybe just put some garbage into R0 and say, yeah. Okay, so suppose you're typing in the email program and it's trying to read characters to type into the message. Is it forever stopping and throwing you blue screens and saying, I'm sorry, I expected the next character, in your message, but you didn't give it to me, so I'm going to stop running the email program. So even though doing that sort of, I'm sorry, your program can't work correctly, is an option, that's probably not the option that the user would want. What do you think the user would like to have happen? What's the user's intent when he typed in read key? Yeah?
Since he just wants to type and doesn't care about how the computer works, he just sort of have the program stop running until he gets here.
Right, so remember we've transferred control to the kernel when we want a character, and it can simply delay returning to that program until there's an actual character to be returned, because that's sort of the semantics of read key. You know, this instruction says give me the next character, so there's really no point in continuing until there is a next character. And then, you know, in a modern system when there's lots of processes to run, we can go on and move somebody else. So we're going to look at the software that accomplishes that sort of high-level goal, which is occasionally we return a character if we have one, but if we don't, the notion is to sort of stall and go do something else, and we're going to see how that might work. Okay, so we already talked about how the keyboard handler, you know, there's a hardware device that typically sits in some sort of I/O address space. Maybe that's a part of the actual hardware address space, the virtual memory physical address space of the kernel. It can reach out and, you know, it accesses a particularly magic I/O address that, or in some machines there's actually separate I/O instructions as opposed to load and store, which go off and get some information. We can go fetch that from the keyboard buffer and put it into the kernel buffer, and away we go. So the kernel buffer is just a standard array. Alrighty, and then the handler's job is to simply, you know, read that and stick the character into the buffer.